In southern Africa, there is a wall that has been standing for over 700 years, without a single drop of mortar holding it together. Every stone in that wall was cut, shaped, and placed by hand, fitted together with such precision that the wall has survived 7 centuries of weather, seismic activity, and time without collapsing. No cement, no mortar, no binding agent of any kind. Just stone, cut and placed with an understanding of weight, balance, and structural distribution that modern engineers still study today. This is Great Zimbabwe, and what its builders accomplished was not luck, it was engineering. The dry stone wall technique used at Great Zimbabwe, known as Zimbabwe-style construction, required builders to understand how to distribute the weight of a curved wall without any adhesive material to compensate for error. Every stone had to be shaped precisely enough to interlock with its neighbors, and the overall structure had to be engineered so that the wall's own weight and curvature kept it standing, rather than collapsing outward under the pressure of its own mass. The famous conical tower at Great Zimbabwe and the great curved enclosure wall that surrounds the site are not just impressive in scale. They represent a sophisticated understanding of structural physics, achieved without any of the materials modern construction relies on. Modern structural engineers have taken these walls seriously enough to study them with the same tools used to analyze contemporary construction. Research teams have built computer simulations using distinct element modeling, calibrated against full-scale physical wall replicas, specifically to understand the structural behavior of Zimbabwe-style dry stone construction, including why certain sections eventually bulge or fail over time. That a wall built without mortar, centuries ago, is rigorous enough to warrant this kind of modern computational analysis is itself a form of recognition. The builders of Great Zimbabwe achieved this without modern mathematics, using accumulated practical knowledge refined and transmitted across generations of skilled stonemasons. But Great Zimbabwe is only one example of a much larger pattern. Across the African continent, architectural traditions developed solutions to engineering problems that the modern construction industry is still working to solve. Consider the problem of keeping a building cool in extreme heat without using any mechanical cooling system. This is, today, one of the central challenges of sustainable architecture. A field actively searching for ways to reduce the massive energy consumption of modern air conditioning. Across West Africa and North Africa, architectural traditions developed passive cooling techniques centuries ago that solved exactly this problem. Thick mud brick or rammed earth walls, often a meter or more in depth, absorb heat slowly during the day and release it slowly at night, keeping interior temperatures remarkably stable despite extreme outdoor temperature swings. Small, high-placed windows limit direct sun exposure while still allowing air circulation. Courtyard-centered designs create a column of cooler air that sinks into the living spaces, drawing hot air upward and out through strategically placed openings. In some North African and Saharan architectural traditions, wind-catching tower structures channel prevailing breezes downward into interior spaces, creating natural ventilation without any mechanical assistance. These are not simple or accidental design choices. They represent centuries of accumulated environmental engineering knowledge, an understanding of thermal mass, airflow dynamics, and solar orientation that was refined through direct observation and generational transmission long before anyone had formal terminology for these concepts. Today, this approach is called passive design, and it is considered cutting-edge in sustainable architecture. Architects and engineers working on energy-efficient buildings actively study traditional African building techniques as models for reducing modern energy consumption. The field essentially rediscovered and is now trying to scale what African builders had already solved. The Great Mosque of Djenne in Mali presents one of the most remarkable examples of architectural philosophy in the world. It is the largest mud brick structure on Earth, and it has been continuously rebuilt and maintained on the same foundation since the 13th century, with the structure in its current form dating to 1907. What makes Djenne extraordinary is not just its scale, but its design philosophy. Mud brick architecture requires maintenance. The exterior plaster erodes with seasonal rains and must be reapplied. Rather than treating this as a flaw, the architectural tradition surrounding Djenne built maintenance directly into the social and religious life of the community. Each year, the people of Djenne participate in a communal replastering festival, repairing and renewing the mosque's surface together. The building's longevity depends not on materials that resist all decay, but on a sustainable relationship between architecture and community that ensures ongoing care. Modern sustainable architecture increasingly emphasizes exactly this principle, that buildings designed for long-term community stewardship, rather than materials engineered to require zero maintenance, often prove more durable and more environmentally sound over time. Djenne has been demonstrating this principle in practice for over 700 years. In Ethiopia, the rock-hewn churches of Lalibela present an entirely different category of architectural achievement, one that required a completely different kind of engineering precision. Built in the 12th and 13th centuries, the 11 churches of Lalibela were not constructed by stacking material upward. They were carved downward, directly out of solid volcanic rock, each church excavated as a single continuous piece from the surrounding stone. This technique, sometimes called negative architecture or subtractive architecture, required a level of advanced planning that conventional building does not. When you build upward with stone or brick, a measurement error can often be corrected by adjusting subsequent layers. When you carve a church downward out of solid rock, there is no such correction available. Every measurement, every angle, every architectural detail had to be planned with complete accuracy before a single cut was made, because removed stone cannot be replaced. The builders of Lalibela had to hold the entire three-dimensional structure of each church in their minds, fully realized, before beginning excavation. The result is a series of churches with multiple stories, interior chambers, windows, and elaborately carved architectural details, each existing as a single piece of rock separated from the surrounding stone by a deep trench, connected to the others by an underground network of tunnels and passages. Architectural historians who have studied Lalibela describe the planning and execution required as representing one of the most demanding feats of architectural engineering in the medieval world, executed with a margin for error that approached zero. The pattern across Great Zimbabwe, the passive cooling traditions of West and North Africa, the Great Mosque of Djenne, and the rock-hewn churches of Lalibela is the same pattern this channel keeps returning to. These were not primitive solutions, applied because more sophisticated options were unavailable. These were sophisticated solutions to genuinely difficult engineering problems, developed through systematic observation, generational knowledge transmission, and a depth of environmental and structural understanding that modern engineers, working with modern tools and modern mathematics, continue to study and learn from today. The history of architecture taught in most institutions moves from ancient Egypt, briefly, to ancient Greece and Rome, to the European medieval cathedral, to the modern skyscraper, treating sophisticated structural engineering as something that happened primarily in Europe, with occasional acknowledgement of Egypt as an exception rather than as part of a broader African pattern. That history leaves out a wall that has stood for 7 centuries without mortar. It leaves out cooling systems that worked for 1,000 years without electricity, that modern architects are now racing to relearn. It leaves out a mosque that has survived 700 years because an entire community decided, generation after generation, to take care of it together. It leaves out churches carved downward into solid rock with a precision that left no room for correction. Your ancestors solved engineering problems that professionals are still studying today. With access to mathematics and materials science your ancestors never had. They solved them anyway, through patient observation, accumulated knowledge, and a relationship to materials and environment that modern architecture is only now beginning to fully appreciate. The wall is still standing. The mosque is still standing. The churches are still standing. They were never waiting to be discovered. They were waiting to be acknowledged.